Hello, and welcome to Weapons of Math Instruction. This is the fourth in my series of videos on uncommon integration techniques. And in this installment, I'll be continuing the discussion from my last video on how to use power series as an integration technique. If you watched the last video, you know that the example was kind of long. And I really want to show you the example in this video too, so I split them up into two videos. If you haven't watched the last video, I encourage you to do so. I'll post a link to that video in the description. The integral that I want to show you is down here in the fourth segment. It's kind of long too, so I'm going to spend the first three segments obtaining some preliminary results because I don't want to have to do them midstream while I'm calculating the integral. Having the results of these preliminary steps will really clean up the calculation in the fourth segment. If you're a Calculus 2 instructor and you'd like to show this integral to your class, you might consider assigning the three preliminary steps as homework in the prior class period. I know I would. In the first segment, we're going to calculate this limit. The limit as t approaches 0 from the right of t to the n plus 1 natural log of t. So here's the limit for reference, and the n in the exponent here is a natural number. So on first inspection, we see that as t goes to 0 from the right, t to the n plus 1 goes to 0, and the natural log of t goes to negative infinity. This is an indeterminate form. We can't apply L'Hopital's rule straight away, but we have a standard method for massaging limits like this so that we can. And that standard method is to rewrite t to the n plus 1 as t to the minus n minus 1 in the denominator. And this limit goes to negative infinity over infinity, and now L'Hopital can come to the rescue. So taking the derivative of the numerator and denominator, I get 1 over t on top, and I get t to the minus n minus 2 on the bottom. And here I brought t to the minus n minus 2 as t to the n plus 2 upstairs. So next I'll multiply these two together to get t to the n plus 1 in the limit. And this is not an indeterminate form. We can just plug the 0 in to get 0. So this limit is 0 for all natural numbers n. And this completes preliminary step 1. In this segment, I'll calculate the integral from 0 to 1 of x to the n ln of x dx. So here's the integral for reference. And once again, n is a natural number in this calculation. And we'll integrate this thing by parts, using these parts here. So I've chosen u equals ln x, which forces dv to be x to the n dx, and then we calculate the other parts. du is 1 over x dx, v is 1 over n plus 1, x to the n plus 1. Now this is an improper integral because the integrand is not defined at 0. So when I handle u times v over here, I'll take the limit as this parameter t approaches 0 from the right, and then I'll evaluate this thing from t to 1 instead of 0 to 1. And I won't bother taking a limit when I integrate v du, because once I simplify this right here, the integral won't be improper. So let's clear these parts off the slide and continue working. Here I've pulled the 1 over n plus 1 outside of the bracket, and I've evaluated the bracket to get 0 minus t to the n plus 1 ln of t. And in this step, I've dropped this 0 and I pulled this negative sign all the way to the left. And over here, I've integrated x to the n to get x to the n plus 1 over n plus 1. And we already had an n plus 1 there, so now that's n plus 1 squared. So, we saw in the last segment that this limit right here is 0. And if I evaluate this bracket, I get 1. So substituting those values into the right-hand side, I get my result. The integral from 0 to 1 of x to the n ln of x dx equals negative 1 over n plus 1 squared for all natural numbers n. This completes preliminary step 2. In this segment, I'll decompose 1 over n times n plus 1 squared into partial fractions. So here's that rational expression for reference. And here's the partial fraction decomposition. I have one partial fraction corresponding to the linear factor n, and I have two partial fractions corresponding to the repeated linear factor n plus 1 squared. And we got to find a, b, and c. And you know the drill. Multiply both sides by the least common denominator of the partial fractions, n times n plus 1 squared. And here's what we get. And next we'll plug in some convenient values of n. So first I'll plug in n equals 0. So this term goes to 0, and this term goes to 0, and I'm left with a equals 1. Now plug in n equals negative 1. So this term goes to 0, and this term goes to 0, and I'm left with c equals negative 1. Now there are no other values of n that are going to make any terms on the right side go to 0, but since we know the values of a and c, we can plug in whatever we want. So I'll plug in n equals 1. When I do that, I get 1 equals 2 squared plus 2b minus 1, and that's easy to solve for b. we get b equals negative 1. So our partial fraction decomposition for this rational expression is 1 over n minus 1 over n plus 1 minus 1 over n plus 1 squared. And this completes preliminary step 3. Okay, on to the main enchilada. This is the integral that I want to show you using power series as an integration technique. So here it is, the integral from 0 to 1 of the ln of x times the ln of 1 minus x dx. Straight away, we'll bust out the Maclaurin series for the ln of 1 minus x, and that is negative sum from 1 to infinity x to the n over n. And in case you're wondering, how on earth did you know to use this technique? It's simply because I don't know what else to do. And I've got a series expansion for this factor right here. If anyone knows how to do this integral using standard calculus 2 techniques, let me know in the comments. Or better yet, make a video. I'm having a ball doing this, and I want to see you get in on the fun too. So here I've substituted the Maclaurin series in for the ln of 1 minus x right there. And here I've pulled the negative sign all the way outside, and I've reversed the order of summation and integration. And finally I pulled the 1 over n outside the integral because it doesn't depend on x. And what's this? Why, it's the integral from preliminary step 2. It's almost like I knew it was coming or something. We know what this is. This is negative 1 over n plus 1 squared. And so for this integral, I get the sum from 1 to infinity of 1 over n times n plus 1 squared. Now the integration is done, but who the heck knows what the sum of this series is? Well, I do, but I'm not going to tell you yet. So this rational expression is the same one that we decomposed in preliminary step 3. So I'm going to use that decomposition now. And there it is. In this step, I've broken this single sum up into these two sums. Why? I'm glad you asked. I'll tell you why. It's because I know how to sum them individually. First thing I'm going to do is change the index from n to k, where k starts at 2 instead of 1. Now, bumping up the lower limit of the sum n by 1 means I need to replace n with k minus 1. I have to bring it down by 1, which is what I've done here. So 1 over n minus 1 over n plus 1 becomes 1 over k minus 1 over k, and 1 over n plus 1 squared becomes 1 over k squared. Now, this guy here I recognize as a telescoping series. And this guy looks almost like the series from the Basel problem, which I showed you in the last video. I say almost because this series would need to start at k equals 1 for this series to be equal to pi squared over 6. But there's a fix. Here, I've added a term to this sum, namely the k equals 1 term. Now, the k equals 1 term is 1 over 1 squared, which is 1. So I've essentially added 1 to this expression. And you can't just go around adding 1 to things willy-nilly. So here, I've subtracted the 1. So it's all good. Now this telescopic series sums to 1. You can see that clearly by listing out the first several terms of the series and observing all the cancellations that take place. Only the 1 survives. In fact, this is probably a worked example in your calculus book. And this series sums to pi squared over 6. So what I have is 1 minus pi squared over 6 minus 1. And if I simplify this thing, I get my answer. The integral from 0 to 1 of the ln of x times the ln of 1 minus x dx equals 2 minus pi squared over 6. And that's it. Thanks for watching Weapons of Math Instruction, and I'll talk to you again in a couple of days. Bye-bye. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.